Okay, hi everyone. I think it's time to start. 5:10. My name is Yves Mabiala. I'm from Thales in France. I will explain a bit later what we are doing at Thales. In this talk, we are going to present you what we are doing in sequence learning, and especially in the application of recurrent neural network for sequence learning. So the outline, the agenda, I'm going to spend a few minutes talking about what we are doing at Thales, why we make use of big data, especially Spark in that context. Then I'm gonna explain you what is sequence learning, what are the difficulties when you want to learn the dynamics of a sequence. How we use basically deep learning and especially recurrent neural network that can be deep or not for sequence learning. I will detail in a slide what is the implementation of deep learning that we built on top of Spark, and we'll end with some use case, especially one in predictive maintenance that Pierre, my colleague, will present, and another one in natural language processing, which deal with sentiment analysis. So as I told you, a few words about Thales. So basically, for those who don't know Thales, Thales is quite a big French company, actually, which builds systems in different domains, transportation, aircraft equipments, a lot of military stuff too, satellites, security. And basically, all of these systems, they produce a huge quantity of data. So I've written a couple of examples of that. For example, in the transportation domain, we produce what we call ticketing systems. So for example, when you enter transportation, you have to use your badge, and we collect this data in order to analyze it. In security, we got data, for example, from radar traces. So we got trajectory from plane, from boat, etc. We got also data in cybersecurity domains, network logs, for example, which is quite massive. We also have got data from satellite domain, photos, videos. So all of this data is basically very massive. Of course, network logs can be petabytes of information. The same goes for satellites. It's very heterogeneous and extremely dynamic. And something important in that is that we got to understand the dynamic of the monitored phenomena in order to make a relevant analysis. For example, in the network logs, we have to analyze in a sequence manner all the operation that a given user's made. It's not random observation, it's not independent. You have to use and to analyze the overall sequence in order to learn from its behavior. So what is sequence learning? Basically, sequence learning refers to a set of machine learning tasks where a model has to either deal with sequences as an input, as an output, or actually both. I'm talking about sequences. There have been a couple of talks, especially one yesterday about time series. Time series, special case of sequences where time plays a great role, but you got some other type of sequences. For example, in genomics, you got sequences of genes. There's no time in that. This is the sequences. And that's something we also study. So the goal in sequence learning is basically to understand the dynamic of a sequence in order to classify the sequence, for example, in order to predict or to forecast, for example, in time series application, or to model the sequence, for example, in language modeling. Some of the typical application is not exhaustive, but those are typical applications. In text, for example, one of the most common tasks is to classify text. So basically, it could be, for example, sentiment analysis. So you have a text which is either a sequence of words or a sequence of letters. You have two levels of sequence when you are dealing with text, and you want to classify either in positive or in negative. Or another task in the textual domain is to general textual description of images, for example. That's something we call image captioning. You got an image, and you want to build a textual description of this image. So, for example, a cat sitting on a chair. This is a common task too. So in this case, the input is an image. It's a fixed size input, and you want to be able to produce a sequence as an output. In video, for example, video classification, video is a sequences of images, or in speech, speech to text is a great example of sequence learning. So how is it typically handled? Taking into account the dynamics is very difficult actually, and sometimes people, they do not bother. For example, one of the main example is in the natural language processing. Basically, one of the most common approach to analyze text is to use an approach called bag of words. So basically, you take a text as an input and you will vectorize it, either using what we call one-hot encoding or just counting the number of occurrence of a given word in the text. So I made 3 examples that are in the slide. For example, the last one, the cat is young. I vectorize the example, and the result is a vector, 1 or 0, and I put 1 for when the word is present in the sentence. For example, the, is, young, and cat. Very simple example. So this is okay for certain tasks where you can classify just using the words, not the sequences. But this is a problem for certain other tasks where sequences play a great role. For example, in sentiment classification, you can have the same words in 2 phrases. The order will have an impact. It could be positive in one example and negative in the other example. So you have to take into account the sequence in this case. So either they do not bother or they use popular statistical approach. So in the talk yesterday, people have talked about autoregressive approach for time series forecasting. That's something very popular when you are dealing with time series. There are other statistical approach, including Markov model, which is one of the most popular approach for sequence learning, either for prediction, for forecasting, for modeling, or for classification. But the fact is that using Markov, which could be hidden or not, using Markov model has some constraint. In the strict version, there is what we call short-term dependency at order 1. So basically, x, which is an observation of a sequence, at index k, it only depends. It only depends of the last observation. So it only depends of xk minus 1. So that's a big problem when you have longer dependency. Another problem in Markovian modelization is that it's not very scalable, because one of the main inference algorithm for hidden Markov model, for example, is called Viterbi algorithm, and it basically scales in quadratic cost of the states. For example, if the state is a vocabulary, for example, a word of a text, it can be very large. And you have a quadratic cost for inference on sequence of sequences using Markov model. So it could be a problem. So you have to find better approach. So what is the link with artificial neural networks? I'll go fast on that. Artificial neural networks is basically a set of statistical models which have been at first inspired from the brain. So it's basically composed of multiple neuronal layers. Each of these layers apply a transformation of its input. You can view this as a projection of the input onto a new feature space. So basically, when you stack multiple layers, you will have more and more complex feature space. And the goal is to learn, for example, either to predict or to classify from the input. When you got more than 2 layers, 2 hidden layers, we often refer as deep learning. So basically, deep learning is basically artificial neural network with many layers. In fact, more than two hidden layers. It's not only applying deep learning. It's something like it's more like a paradigm shift. For example, in image classification, what people tend to do before is they got the image they build some features from the image using traditional transform. It could be wavelet transform. R features, for example, have been very used in image classification. And then they use a classification model, such as logistic regression or things like that. With deep learning approach, you are able to infer, to construct features that are appropriate for classification or for prediction. So there's no need for certain tasks to build those type of features. So artificial neural networks are basically a set of transformation and activation operations. So the most popular one are affine transformation, which is basically a scalar product between the input x and a weight w. Popular activation are sigmoid and tangent hyperbolic. And when you use affine and sigmoid or tangent, basically this is what we call a multi-layer perceptron. This is something that has been introduced in Spark, I think in version 1.5 or something like that. So it's available in Spark ML package. But you got also other transformation layer. You got convolutional, for example, which is very popular in image, in the image domain, where you will apply a convolution operation on the input. Input which can be either 1D signal or a 2D signal in case of images. So basically what you will learn is special features that can be used then to classify or to predict. Another type of layers that we will detail in this presentation is recurrent layer, where you will introduce a recurrent part in the neural network in order to learn features related to the dynamic of a sequence. And the objective is to find the best way to minimize the difference between the predicted output and the labels that has been used for the learning of the neural network. So a few words, I'll go fast again on that, on recurrent neural networks. So basically, at the top left, you got a classical neural network. X is the input, for example, an image, fixed size input. Y is the output, fixed size label. For example, I get an image I want to classify. It's a cat, for example. On the top right, you have a recurrent neural network. So what you can see on the schema is that I introduce a loop from the output to the input. And you got the expression yk, which is the output at index k, not only depend on the xk, which is the input at index k, but also on the output at index k minus 1. And if I unrolled, what we call unrolling the neural network through times, at the top right, you get the representation of the neural network. So you can see, for example, that yk not only depend on xk, but also on xk minus 1, xk minus 2, xk minus 3. So using this, you are able to extract some important information related to the dynamics. So basically, neural networks are able to cope with varying size sequences, as I told you, either at the input or at the output. And you got something like 3 configurations. One, which is called one-to-many. So you got a fixed size input, and you want to generate a sequence. So it's the example at the bottom left. For example, image captioning. You got an image, you generate a textual description of this image. On the middle, many-to-many, you got a sequence at the input, and you want to output a sequence too. For example, in speech-to-text, you got a speech, which is a sequence. You output a text, which is also a sequence. And many-to-one text classification, you got a text, sequences either of words or letters, depending on the modelization that you do, and you output a label. For example, positive or negative if it's sentiment classification, for example. But training recurrent neural networks is very, very difficult, actually, or were known to be difficult, at least. 2 reasons for that. You got more weights to learn, so it's way more computationally expensive. So you need accelerator to learn this model. And often, people have used CPU libraries, such as BLAST, for example, which is an accelerator for linear algebra on CPU, or even GPU. But another thing, another constraint, very important constraint, is that you have to scale. Basically, if you have a lot of weights to learn, you also need a lot of data to converge, to learn these weights. So it also speaks for scalability over clusters, over big data architectures. And that's basically why we choose Spark. And something that you have to know, something that has been mentioned in the talk, I think, this morning, is that basically, popular open source libraries such as Theano or TensorFlow or Caffe, they do not offer a distributed version in the open source version. So that's something you have to build to get the scalability over big data architecture. And another thing from the theory this time is that simple recurrent neural networks, they are basically unable to learn long-range dependency. That's something that has been actually formalized, I think, by Grave in 2014. So basically what it means is that at a given time t, RNN does not remember what happened before t minus n. That's something which is due to a phenomenon called vanishing gradient, where we backpropagate the gradient. We have to backpropagate in the different layer, but also in time, from yk to x k minus n. And the more we backpropagate through times, the weaker the gradient gets. And basically, after some times, it gets null. So you're unable to infer long-range dependency. So that's basically why a new RNN architecture have appeared. Two, actually. There are more than that, but there are two here. One which is called LSTM. It's basically appeared in 97, I think. And another one called GRU, which has appeared in 2014. So basically, if we look at very quick at the equation on the right, yk is now a function of zk and what we call the candidate activation function h till k. Zk is what we call the update gate. Basically, it controls how much the information flows through times, and basically enables to learn dependencies at different time scale. So basically, using that and using Rk, which is the reset gate in the h till k, you are able to learn dependencies at different time scale, which simple RNN cannot do. So the implementation in Spark, so we basically have an implementation of multi-layer perceptron in Spark, as I told you, from 1.5, I think. Spark got in a ML package multi-layer perceptron, but we got to go further than that. So we re-implemented some other blocks, some needed blocks, in order for a recurrent neural network to work. Three categories. From the layers, so affine, convolutional, recurrent layers, simple and GRU. Some activation function, sigmoid, tangent hyperbolic, and what we call rectified linear activation, and also some better optimizer to go further stochastic gradient descent. So we use what we call RMS prop and ADA delta optimizer. We are also able to launch this on CPU, of course, but we've worked a lot on the GPU backend. For those of you who are familiar with Theano, for example, you are able in Theano to change in a single sentence the execution either on CPU or in GPU. That's something that we want to be able to do. And we work a lot on that. And it's, of course, fully compatible with existing deep learning library in Spark ML. So a few words about the performance of a very small cluster. You got a very nice scalability. For example, 6-node cluster, you got 5.46 average speedup. Of course, you got some loss. It's mainly due to the communication constraints. But it scales very well, and it's about the same speedup as machine learning, as multi-layer perceptron in Spark. So I'll leave the floor to Pierre, which will present you some of the use cases.
Okay, thank you. So I'm going to, I think it doesn't work. I'm going to present you some use case that we did with the Spark implementation that we get before with Eve. So the first use case is about predictive maintenance. So the goal in the end is to, so Thales is building a, is building some different, is building system in different domains in transportation, like ticketing. You can see in the metro, all the passage of badge in the metro is about ticketing, the controlling, and in defense there are radar. And satellites. So the aim is to collect the data that have come from the system installed before by Thales, and to implement some Okay, I can use it. And to implement some use of RNN, actually, in order to take into account the dynamic, separate what?
Yeah?
Oh,
I have to go further.
okay, thank you. Yeah, thank you very much. So yeah, the aim is to collect the data from the system built by Thales and to use to use the Spark implementation that we get of the RNN in order to take into account the dynamic of the system that are under this. I don't think it's that. Whoa.
You have to talk louder. The gain, they have to turn up the gain too much, and so there's feedback. So if you talk louder, they want to turn up the gain as much for us to hear it, and there'll be feedback.
Okay, so I can skip it. So yeah, we collect the data from the system installed before by Thales, and we use the RNN that we just implemented in Spark in order to take into account the dynamic of the system. And so the aim in the end is to get a better maintenance of the services. So from now, we are only able to plan some, so to plan the maintenance. So we say that we are going to make a maintenance on the system every week or every month, and we don't know what we are going to do on the system. We just check, is it still working or not? And if there is an issue, we are going to see it, and we are going to make an alert and to repair the system. Now, what we want to do is to make some alert maintenance in order to orient the expert and to say, you should see what is going on with the system at that time and on this kind of issue. So the aim is to go from an expert detection, that's what we say, to an automatic failure prediction. So the important word is that we are going to make prediction. And we are going to know where we should look, so it's why it's written localized reparation. So the system is going to orient the expert to the good reparation to do. And yeah, in the end, we got to see the early signs of a subsystem failure. So we're going to say this system is going to stop working in 1 month on this kind of problem. So that's why it's written HUMS for Health and Usage Monitoring System. So how we're going to do that on some kind of data? So the first use case is predictive maintenance. Where on a real system, we got, say, 20 sensors that crash a lot of value, maybe every 5 minutes. So we got 20 value every 5 minutes. And they are labeled with the fact that there is or not a system, maybe in the next hour. So you say, here is the curve of some sensor value, some sensor. So you can say maybe it's the temperature or something like that. And not sure. And this one I cut off?
Here, we're going to try.
Okay. Thank you. Yeah, it's working. A little more. So, yeah, we got 20 sensors. We got so value every 5 minutes. And we label the data with the fact that 1 hour after there is or there isn't a failure. So we say if the temperature in a really simple system, maybe a chemical equation, we can say if the temperature is more than, say, 100 Kelvin, it's going to fail. So here is the temperature. I mean, say it's the temperature, it may not be, but and we label the system with if the temperature is going up to 100 Kelvin, then there is a failure 2 hours after. So we take 3 hours of data, it's a small piece of data, and we predict the probability of a failure in the next hour. Of course, you can do what you want with that, so you can take maybe 5 hours of data and say it's going to be a failure in the next few days and not just in half an hour. So if we just used MLlib, that is currently used now, we're going to be able to make a logistic regression. So here is the data, which is sequence RDD. and we use the data to make a logistic regression, but we cannot take into account the dynamic of the system. We can just say, if the temperature is going more than 100 Kelvin, then there is a failure. We cannot say, if the temperature is increasing or is decreasing, then there is going to make a failure. So in order to do that, you need to take into account the dynamic, and that's why, as Yves said, you need to use RNN. I mean, it's a solution to take to use sequence learning. So here, that's what we made using our implementation in Spark. So we implemented recurrent net learning, and here you can see that we fully construct the RNN. So there is a model that we construct build by build, and you need to think of our implementation as a toolkit. So you can pick up some part of layers that you want to use in your model, and here that's what we do. So we use, for example, gated recurrent layer because it's what worked here, and Yves said that it was before that it was one of the better layer. Then we use after dropout layer, and you can really make every layer with every type that you want to construct any recurrent neural network. So with a logistic regression, that's what we would have used with MLlib. We would have a 70 detection with 70% of accuracy. So it means that there is 30% of false positive, so false alarm. And with recurrent neural network, there is a 85 detection, 85%, so it's a little more. And there is 75% accuracy, so it's still better. So I will let the second application case to Yves.
Yeah, I'll go fast on the. Yeah, maybe I'll take the mic. Otherwise, you have to activate the. Okay. I'll go fast on the second use case because I think we're running a bit out of time. But it's something I talked about on the first slide, I think. Sentiment analysis on textual data. So basically the goal of this use case will be to demonstrate the use of the sequentiality information contained in text, and to demonstrate the advantage of modeling the text as RNN over simple logistic regression or SVM or whatever. So basically the context is that we have built social network analysis application inside TELUS, so we are able to collect information coming from blogs, forums, Twitter, etc. And what we do is basically to both analyze the content of the information and the relation between actors, for example. So there are multiple axes of analysis. Actor community detection, we could have spoken about that, but that's not the what we are going to talk about. Text clustering, that we also do that in Spark, but we'll focus on sentiment analysis on the collective test. The learning dataset on which we made this experiment is basically one of the well-known dataset for sentiment analysis on Twitter. So it's basically the sentiment 140 plus the Kaggle challenge. So you got something like 1.5 million labeled tweets, and it's 50% positive and 50% negative. And the idea of what I'm going to show you is to compare bag of words plus a standard classifier approach. So we use three: naive bias, support vector machine, and logistic regression, which are both available inside MLlib versus recurrent neural network. So you got the code of an SVM at first, how we create the bag of word and train the SVM, and at the bottom you got the text, the code for the recurrent neural network. So it's kind of encapsulated. You got just the function learned recurrent, but it's somewhat the same as what has been displayed before. You got GRU layer, then dropout, and then dense layer. And the idea is to compare the performance of both approach. So on the right, you got the size of the training data set from 100 to 700,000. And you got all the results for the 5 methods. So what you can see basically is that when you have not a lot of data, I would say less than 100,000, basically it has no use to use RNN. you don't have enough data to estimate all the weights in a GRU layer, for example. So if we take the example of 10,000 tweets on which we learn, the performance of RNN is 72, that's 3%. And the single logistic regression is better. But as soon as we got enough data to estimate all the weights, for example, 700,000, we can see that there's an advantage of using RNN. We got 84.1% precision using RNN compared to 78, that's 3% using logistic regression. So that's what I told you. It's better, actually, when you have enough data to estimate all the weights. So this is the use case we wanted to show you. We have other use cases, especially in video processing, where we combine convolutional neural network and recurrent neural network in order to extract spatial features using convolutional, and then recurrent to track the dynamics between images. And we use that especially for anomaly detection in video surveillance. So I think this is the end. We are running out of time, so thank you for your time. And if you have any question, we will be happy to answer. Thank you. Yeah.
Did you open source the library?
Not yet. Hopefully, we are going to be able to open source, but the decision is not ours. But yeah, I would like to. I would like to. Yep. Yeah, actually what we use, I think it's on this slide, we use the same approach that is in Spark ML, which is data parallel for now. So basically the parallelization is made on data. I've not described this, but at the first, when we instantiate the model is stored on the driver. And what we do when we iterate to learn is basically to broadcast the model to all the workers, and each of the worker will learn the gradient of the error and will put the gradient back to the driver for the update. So it's data parallel, but we could also have gone further and implemented model parallel. Well, a piece of the neural network will be stored on a given worker, another piece on another one, etc. But for now, it's only data parallel. Yeah, exactly. Yeah.
Go higher than one
One
layer?
layer of recurrent?
Go higher than one here.
One hidden, yeah, of course. In the example, so I don't know if that fully answers your question, but in this example, for example, we got more than one layer. We got one recurrent layer, which is this one, and we got, and we got two dense layers, which are neural networks, which are dense layers. So we got one hidden layer, but we can go further, actually. We can stack the recurrent layer, but also the dense layer, and we go further for some context. In this context, it's not an advantage to add layer. It's quite simple, actually. It's time series. We can modelize the dependency using only one recurrent layer. But for some other type of application, we stack recurrent layer in order to have better result, of course, yeah. Yeah, exactly. Yeah, it definitely applies. You're absolutely right. I think it was here. It applies to neural network in general. One of the main problems when you're using SGD, for example, simple SGD, is the learning rate. Basically, you got to set a learning rate which is fixed. There are approaches which use momentum, for example, which are a bit better. But for our use, we found that RMS prop and ADA delta are better. What they basically do is that you can think of local learning rate for each of the weights, basically. So it's better to use those kind of optimizer than standard HGD, of course, yeah. Yeah?
How many nodes can you scale?
To how many nodes?
Yeah, how many nodes can you
In the cluster or in the? Yeah. I think it's infinite. We did not test on many nodes. I think we went up to something like 30 nodes, and the ratio, the speed up ratio, was about the same. Mostly because we use standard Spark communication, so it's synchronous, contrary to what has been presented in the morning, which was asynchronous communication. The overhead here is, I would say, constant on the number of nodes. So we can scale, but it depends on the data, of course. If you got small data sets, it has no use to scale, and at some time you will find that you won't gain anything to add nodes. But if you got large data sets, it has a benefit to use a bigger cluster, of course. Yeah.
Can you comment on the computational performance of the network in comparison to the other methods like boosting, training, and prediction?
For the, you mean the statistical performance or the learning time?
Time.
The time, okay, yeah. That's something we didn't mention, of course. But in this result, for example, the neural net, which is a perceptron, it's actually only a one-layer perceptron. So it's something like a logistic regression. But if we instantiate a GRU, for example, you have to estimate much more metrics. You got, I think, 8 metrics to estimate, and it's much longer of course, to learn. So I think the ratio here is something like 4 or something like that in time. So that's also something you have to consider. Is the benefit worth it or no? It's definitely longer to learn.
So for the example that you have 100,000 records, how much time in terms of absolute numbers?
For 100,000 records, it's quite. I think it's quite quick, depending on the number of iteration. I think it's less than a second for an observation. Typically, when you have small data set, you won't do mini batch or gradient descent. You will do full batch under this small data set, and it takes, I think, less than a second to compute the gradient and then send back to the driver. So it's quick. It's quite quick. It's Scala. We only use Scala API, so it's Scala there. Okay, thank you for your time. Thank you.